now we switch to a completely different topic. Now it's the time to resume our knowledge on quantum mechanics, and it's the time to speak about semiconductors. So far we have spoken about linear components, resistor, capacitor, inductor, and also linear amplifiers. But now we have to speak about this because it's very important. It's the crucial step in electronics to be able to discover and manage semiconductors. Semiconductors are this quintessence thing that makes everything that was impossible to become possible. Okay, so when we speak about semiconductors, we speak about a different type of materials, but most of the time this material is silicon. There are also other semiconductors, of course, but let's consider this one. So silicon is a mineral that we can extract from a mine, but it's not good in order to be used as a electronic component. We need to purify it. There are at least a couple of methods. Some of them are also patented, so it's not so clear to the public how the factory will do this. But the principle is that if you, for instance, put a so-called seed of silicon, which is a little piece of crystal, into a melted pot, and you pull up this rope very gently, then a sort of candle will be produced. And this candle is a so-called monocrystal. So it's a big piece of crystal which can be manufactured following the principle that the melted silicon will try to follow the crystalline structure of the seed and to replicate and complete the crystal. Then there is also another way, which is called floating zone. So here you have such kind of cylinder of silicon. You don't see this in details in this picture, but here there is a very thick metal wire, which is a so-called electromagnetic coil. So it's a loop. They put current, alternating current flowing in this loop. It creates an electromagnetic field. The electromagnetic field is captured by the silicon, which is a little bit conductive, and it overheats, so the so-called Joule effects, till the point that it melts, but not completely, only around the ring. So there is this floating zone that can be melted, and there is a sort of osmotic effect. So there is a gradient of temperature between the inside and outside, and the impurities tends to go outside. Then they fall down because of the gravity, and if you move this ring up and down slowly, with the time this process will push out impurities and make them falling down. And so in the end you chop the bottom, and what you get is a rod like this. So it looks small, but it's big in fact. So if you see a cross section, it's kind of 30 centimeters, so it's something like 2-3 meters long, and it's an almost perfect crystal. So this thing is called a wafer, and out of this wafer, actually on the surface of this, so you have to imagine that you can sew, with a saw you can cut slices of this, like less than half millimeter thick, and on top of those wafer we can build the so-called integrated circuits. Then this thing can be cut in chips, which are called the microchips. Microchips. So the microchips are little pieces of silicon wafers, which are sections of silicon rods. So the silicon is like this. It's a solid material at an ordinary temperature, of course. It's organized into crystal. Here you have a representation which shows the outer electrons, sorry, all the electrons, and the outer ones are those ones. There are 4. So this atom, when it's melted together with other atoms like this, will try to create 4 links in order to complete the so-called octet. So 4 are missing, and therefore in order to complete the last orbital it wants to join other atoms like this. So if we try to imagine this three-dimensional tetrahedral structure and from above, like in a flat projection, the situation is something like this. So the material has 4 covalent binds, and a silicon material like this is called intrinsic material, intrinsic silicon. So now we can do one thing, which is called doping. So doping means that with some technological tools, actually quite complicated, it is possible to remove one atom of silicon and substitute for another type of atom. Not everywhere, but in some places. So with a certain concentration of dopant atoms. So this is usually done with 2 types of atom, the phosphorus and the boron. Why they do this? Because they have a property. If we look at the electronic structure of those 2 atoms, the phosphorus has an extra electron and the boron has one missing electron respect to what the silicon has. So the atom, as every atom, is neutral from the point of view of the charge, because the charge inside the nucleus always matches the charge of all the electrons, and so for the boron. So we are not creating extra charge from nothing if we put an atom of phosphorus here in place of an atom of silicon. But when all the other silicons will try to complete the octet in order to reach a more stable solid configuration, there will be an extra charge that are not connected to those bindings, and therefore in principle it can be moved, so it goes in the conduction band. Similarly for the boron, but vice versa. So this boron cannot form the last 4th covalent binding with a silicon, and therefore there is a sort of positive place which is called hole, for a negative charge to be there. So what happens is that because there is some thermal energy, so one of these holes would like to be filled by an electron close, which is close to this potential binding, and then the hole moves from one place to another one, and to another one, and to another one, and to another one. So similarly to the negative charge that can go around in the crystal, in this case, when we dope the material with boron, then we have a equivalent positive charge, which is called hole, that can go around easily. So those two materials are called respectively the N-type and the P-type materials. So why do we need this? For many things, but one which is interesting and the simplest one is to build a device which is called diode. So the diode is like this. It's a so-called PN-junction. So it's a junction between a P-type, a P-doped material and an N-doped material. By junction, I mean a real junction. So those two materials are really welded together. They're not just close each other. So the crystal is not interrupted in this area, which is called the area of the junction. It's a continuous material, a continuous crystal. So what happens is that the excess of negative charges, let's say of free negative charges in the N-doped region, wants to fill the excess of positive holes, free holes in the P-doped region. So when you manufacture this, in a moment at the very beginning there is a movement of charges, and this would create an imbalance in the charge distribution. So again, this is a little piece of P welded together with a little piece of N. The total charge is conserved and is 0, but it's distributed unevenly. For instance, like this, on the left and on the right of the barrier. So now we have to mention something that at this point we don't know. That would be the first Maxwell's law, that tell us that the divergence of the electric field is the charge density rho divided by constant. So this thing, we met this operator, we said that in one dimension it's the first derivative, and this thing is a constant. So this is one of the law of the electromagnetism. So if we consider this and we consider only one dimension, the distribution of charge along this direction, by integrating this we get the electric field, which is minus the gradient of the voltage phi. And then if we integrate this second equation, so this in one dimension was this in one dimension, we get the profile of the voltage. So we discover that by manufacturing a neutral, from the point of view of the charge, device like this, there is a voltage appearing from one side to the other one, which is called the built-in voltage. And with the current technology, based on the phosphorus and boron dopant atoms and silicon, this voltage, when you create a junction, is around 0.7 volts. for silicon. And this is the symbol of this device, which is called diode, with two terminals which are called anode and cathode. So why do we need this? It has an interesting property. So if you connect a battery across it, now I try to make this drawing overlapped to this one. So I take a battery like this, with the positive side on the right and the negative side on the left. So here you have negative charges that goes here, and those negative charges that goes here comes from the battery that moved from the other side of the battery, meaning it will leave positive charges here. So what happens is that if you do this, this region, which is called the space charge region, will increase and increase and increase and increase as you increase the voltage, but no current will flow in this circuit. So there is no current, no carriers of charge flowing from here to here or vice versa. What happens is the charge is just built up on the boundaries. If we do the opposite, if we switch the polarity, we change the battery and we put it like this, sorry, like this, the negative side here and the positive side there, then negative charges here would like to fill the holes in order to neutralize those positive extra charges, and similarly those negative charges will be attracted by the positive pole of the battery and will leave the p-doped region. So this region, space charge region, will get narrow and narrow and narrow and narrow, up to the level that when the battery has a voltage which is greater than this 0.7 volts, the built-in voltage, the one that is there from the beginning when you manufacture this, then the negative electrons here, promoted by the battery, will have enough energy to jump on the other side, and therefore there will be a so-called formal current which flows the other way around, flowing into the circuit. So to summarize this, we have this situation. There are two different situations. One which is called forward bias. So we attach a battery with this polarity, with this polarity plus, like this. This is the anode and the cathode of a diode. I also put a resistor, but let's just forget about this for the moment. So in this condition, the current will flow in the circuit. And if I replace the battery with an alternate voltage generator, so a voltage that goes like this, this is time and this is V of time, then because the current will flow only in forward bias, the voltage drop across this resistor would be something like this, and 0 in the period corresponding to this negative peaks of the stimulus. So we say that the diode in this circuit will rectify the signal. So it operates a transformation which is quite deep. It's non-linear because it's a circuit. You can think of it as a two-port network which takes a sinusoid in the output but does not produce a sinusoid in the input but does not produce a sinusoid in the output. It produces this chopped sinusoid like this. And therefore, I want to stress this point, this is a non-linear device, and for this it doesn't have a transfer function. There are ways of extending the concept of transfer function, like trying to make a sort of Taylor series of transfer function, which is called the Volterra series, and also a way to optimize this, which is closer to the Fourier transform. It's a sort of Fourier transform of Fourier transform, which is called the Wiener series, but this thing is quite complicated and most of the time we don't need at all. But I just want to mention, to stress the point that this device, the diode, is the non-linear device. And then one thing that we can also do with a piece of silicon is the so-called transistor. Okay, so this is quite long, but I think that we can introduce the concept at least to see the very basic behavior of it. So now what we do is we take a piece of silicon, we dope it with a P-type material, the red thing, which is called the bulk. For technological reasons, in order to make a contact between a metal and a doped semiconductor, we need to create a gradient of concentration, which is here illustrated with this P plus region and also an N plus region. So we studied the ohmic conductor, and then now we are studying semiconductors, but in real life it is difficult to make a so-called ohmic contact, because every time you put two things that are different each other, like two pieces of different metals, you always create a PN junction. Okay, we don't speak about this. Now let's concentrate on this drawing. It's a piece of p-doped material, so there is a potential excess of negative carriers of charge, and here we have two electrodes. So one is called the source, the other one is called the drain, and there is a third electrode which is called the gate. So gate, source and drain, and then this third electrode is not attached in contact with the material, but it's very close to it. It's just over a yellow layer of insulator, which is silicon dioxide, and silicon dioxide is glass, the common glass, which doesn't allow an electrical contact to be here, but this layer of oxide is so thin that of course the electric field produced by something attached to the gate electrode, like by means of this battery here, can be felt by the underlying bulk with p-doped material. And so it turns out that if we connect a battery like this with the positive side here, those positive charges at this side will attract negative charges from the bulk, and so we will have the formation of a so-called channel full of carriers that can be moved. So now, to move those carriers, we need to attach an electrode here with this battery, and then we have a sort of resistor between. I draw this with a different color. Let's try this one. We have a sort of resistor here, but we can control the resistance of this channel by acting on the gate, because the gate electrode through this gate voltage will modulate the thickness of this channel, and therefore, if you remember the Drude-Lorentz model of a resistor, it was a cylinder like this and the charge was moving inside from one place to another one. Then the resistance was inversely proportional to the cross section of the channel. So if we can make a channel to become narrow or bigger, then we have a method to modulate the resistance of a bipole. So we reach this condition here with this water analogy, where we have a path for the charge. Here is water, and something like a tap that we can open and close in order to modulate the flux. So how does it work? It's quite complicated, but we can describe from a qualitative point of view. So if we consider this situation, we call this current flowing from drain to source, we call it ID, drain current. It's the current that is flowing in this circuit. So this current depends on the voltage of this battery. The bigger the voltage, the bigger the current. It's the Ohm's law. But we said that we can change the resistance of this channel by acting on the gate voltage. So it happens that when we apply a gate voltage, at a certain point, some negative charges are extracted from the bulk. Remember that there are an excess of free negative charges, and they goes where they feel a positive electric field. They create a thing which is called pinch in this channel. So the channel getting narrow from this point, and the more we increase the gate voltage, the narrower this path will become, and this basically will change the resistance of this channel. It will make it having a bigger resistance. So if we consider that the resistance R is V over I over V is the slope of this curve here we see in this type of charts. So by increasing by changing the voltage here, we can change the slope of this curve. So we reach such kind of situation where the relation between the voltage applied at this battery, remember there is a sort of resistor here, and the current flowing inside this resistor, the law that connects those two things, which in principle is the Ohm's law, is modulated by the voltage applied to the gate. So it's modulated in a way, I mean, the manufacturer of these components makes whatever it can in order to reach this condition, for which at a certain point, after a certain voltage, which is called the saturation voltage, the slope of this relation will change quite abruptly like this. And this happens for different values of VGS. So we have a so-called family of curves, like those ones, which tends to go lower in their mostly horizontal part, the lower we set the VGS generator. So this is the beginning of what we will call MOSFET, which is an acronym that stands for Metal Oxide Semiconductor Field Effect Transistor. So this is a device that is not a bipole, it's a tripole, and has this symbol here. So you have the source, the drain, and the gate. Sorry. Drain, source, and gate. So source is called source because this terminal is considered to be a source of electrons. So electrons will go from this inside the component and out of it, but we know that the formal current flows the opposite way. Okay, so for today that's it. Next time we will start from this and we will try to analyze how this works and why it's very useful in order to make so-called signal amplifiers.